Okay, welcome back. Happy Wednesday. Another Monday, another snow day, another calendar. Grab a new copy of this calendar. Recycle the calendar that I gave you before. It is no longer valid. So today, quiz number 1 is due, so throw it in the folder if you haven't done so already. We're going to talk about something called differential equations today. Officially, project number 2 is now assigned, although I gave it out last time, and I know some of you have already made some good progress on it. So that's that. Good. The project number 2 is due on February 20, which normally would be a week from today, but this coming Monday is President's Day. So I think it's a week from Friday. Yeah. Right. This coming Monday, there's no classes because of President's Day. Really? Yep. 3-day weekends, every weekend. Okay, any questions on the calendar? Okay, something else to mention about the calendar. I know you guys are on page 45 in the packet, but I'm going to jump back to page 3 for just a moment. So, you just handed in quiz number 1. Quiz number 2, quiz number 2 is now officially assigned. This quiz is different from every other quiz for the whole semester in that it is a straight memorization quiz, which you get to take as many times as you wish. The quiz exists on page 3 in your packet. It's right here. I gave it to you on the first day. So what you are going to do is fill in all of these derivative formulas, fill in all of these integral formulas. There are a couple of other formulas down in boxes here at the bottom: product rule, quotient rule, chain rule, some stuff about position functions and velocities and accelerations. Lots of formulas to fill in, all memorization, so you have no other resources that you're going to be using except for your own brain. The good news for you as you study for this quiz is that the answers are on the next page. So you can, if there's any that you're not sure about, look them up, memorize them, learn them. It is time to learn them if you don't know them just yet, and study before you take this thing. So I said you could take the quiz as many times as you want. If you're not happy, you're going to score your own quiz. I give you the answer key, so you're going to grade it yourself. If you're not happy with the grade, on page 4 is another blank copy of the quiz, and page 5 is another blank copy of the quiz. If you want more copies, let me know. I'll print you more copies. All right? So take it as many times as you want. It is due not this coming Friday, but our following class, which is Wednesday, a week from today. And your best score counts, right? So in theory, everybody can get 100 on this. It's just a matter of memorizing, and that's the goal, is to just know these rules cold, okay? Any questions? This is the only quiz where you can't use like an index card or any reference sheet. This is just all you. Questions on the quiz? Okay, so, yes. Yes. You can use that sheet on tests. No, you're going to be using the page 1 of this packet. That's the reference sheet that I'm providing for the tests and quizzes. Okay. Any other questions? Okay, so we're here on page 45. Oh, one other announcement. I was asked to share this with you guys. So in every one of the classrooms, there is one of these blue single stream recycling bins. This is just a little bit of education about what goes in and what does not go in. So we just ask you to think about what is recyclable, what isn't, when you come up here to make your decisions. So recyclable things are clean paper and cardboard, empty glass and plastic bottles, empty cans. Here's a list of things that are not recyclable, including down here plastic bags. I don't expect you'll memorize it, so I printed it. It's right here. So just read the list and decide which receptacle your stuff belongs in. Questions? Okay. All right, so top of page 45 with our daily summary. Let's start with Stefan at the front. Thank you. Haley, number 1. Okay, let's pause right there. So that right there is our very first differential equation. It's just an equation that involves derivatives. Alex. So if direction is changing, then you could make the case that the velocity is changing. So how about constant speed? Are you willing to buy that? Yeah, I think no, I think technically yes. But if the speed is consistent, then maybe we say constant speed and we're kind of abusing the word velocity. In the examples that we're going to be talking about, it's not rotation, it's just like a straight up and down type path. Okay, let's move on to number 2. Let's go to Susanna.
We can get much more complex. We do y double prime minus y prime minus 12y equals 0. In English, we see the function y is the second derivative of y minus the first derivative of y minus 12 times the original function.
Okay, let's pause there. So this is an equation. It involves derivatives, so it is called a differential equation. At the moment, there really isn't any reason that you should think that differential equations are worth anything, but trust me, they are. You'll probably take an entire course in them, but we're just going to spend one day on them now and like one day late in the semester. But looking at that equation, we're looking for a function, y, that satisfies that equation. You want to take 2 derivatives of the original function. You want to subtract the original function, the first derivative of the original function. Then you want to subtract 12 times the original function itself, and somehow magically everything disappears and you get 0. So the question is, what might the solution to this differential equation be, or what might it look like? So here's some examples. Suppose that I just said, okay, well, what if y equals x squared is just something we're going to test to see if it might work? So in order to plug in, we're just going to take our 2 derivatives and see what happens. So first derivative is 2x, second derivative, plane 2. And then we're going to plug that stuff into our equation. So this guy becomes, instead of y double prime, what do we put? 2 minus, instead of y prime, it's the 2x, minus, instead of 12y, we're going to put 12x squared. And we're going to say, is this equal to 0? Now, I trust that you could find solutions to that equation. There's probably 2 different values of x that make that equation true, but that's not what it means to solve the differential equation. That thing is supposed to equal 0 all the time for every value of x, and it doesn't. There's still x's floating around in this thing. So it wasn't true. It was supposed to be identically 0, and it wasn't. Fair? So all that means is that y equals x squared wasn't the solution to the differential equation. All right, what kinds of functions might have a chance? Do you think polynomial, like a bigger degree polynomial? Why no? Smaller degree polynomial? How about y equals 0? All right, so here's our second attempt at solving this differential equation. Let's take our 2 derivatives. I think good things are going to happen here, right? Derivatives are all 0, so then we plug everything into the original. So then instead of y double prime, 0, minus, instead of y prime, 0, minus, what do we put next? 12 times 0 equals, with a question mark, 0. Does it always equal 0? Yes, we have found a solution to our differential equation. Y equals 0. Fantastic. Any other things that might be solutions to this differential equation? Other kinds of functions that have a chance of working? Do you see the fundamental problem with the x squared? Is that when you took a derivative, it became just a different thing, and we were hoping to be able to just like cancel all of these x's and just get 0, but it's not going to happen because when you take a derivative, the power changes, right? So there's no polynomial that's going to work. It's not even like I just need to find a better polynomial. Like it just can't possibly work because when you take derivatives, they change and they won't magically be able to cancel each other anymore. Kevin? Like what? What's good about the guess y equals sine of x? When you take a derivative, when it changes to cosine, but then it comes back to sine, and so maybe there's a chance that like we'll cancel, right? Like my polynomial wasn't going to cancel, but maybe with sine, it would work. So we'll take our derivatives here. Sine becomes cosine. Cosine becomes negative sign. And then we'll plug everything back into that original differential equation just up here at the top. So y double prime is this negative sign. So we're going to grab this guy down here. Negative sign of x minus, instead of y prime, cosine of x minus 12 times sine of x equals 0 question mark. Does it? No, but at least there's some potential canceling here, right? Like we got signs that are going to talk to other signs. So maybe instead of sine of x, we try like sine of 2x or sine of 3x. Because then when I take derivatives, with that sine of 2x, what happens when I take a derivative? It's going to become 2 cosine, right? And so we can finagle with the numbers in the fronts of the sines and cosines. So maybe that's a good candidate. Unfortunately, yeah, the signs, we could maybe get them to talk to each other, but there's this ugly cosine just sitting in the middle, not canceling with anyone. So it's a great guess, but it seems like that one guy in the middle is going to be odd and not be able to cancel with anything. Any other functions you can think of that when you take the derivative, it doesn't change that much, that it would still be a like term? Steve? Yeah, e to the x seems like a good candidate, right? Because when you take derivatives, it doesn't change at all, still like terms. What about e to the 2x? When you take a derivative, it becomes 2e to the 2x and still talks to its partners, right? And so exponential functions are great candidates here because they're all combinable. Okay, so I'm going to present you with a miracle here. I hope you appreciate it. So here's my miracle. I will tell you that one solution to this is plus 3. I'm going to say e to the negative 3x. Okay, so it should not be clear to you why I happen to choose negative 3 up there. But what we should be able to do is check whether or not that's a solution by doing the same process we've just followed. Let's take two derivatives, plug it in, and see if we actually had a miracle here. So y prime equals y double prime equals okay, first derivative. All right, we got a negative 3 popping out from the chain rule. And then when we take another derivative, another negative 3, which is going to become positive 9. Okay, so let's plug back these guys into our original. Instead of y double prime is 9e to the minus 3x. What's the next symbol in our differential equation? Minus, and then we subtract y prime, which is this negative 3e to the minus 3x. And then next, minus 12 times the original y. Minus 12 times the original e to the negative 3x. Equals with a question mark 0. Does it? It does. Everything magically just explodes and disappears. Right? Yeah, I'm really smart. That's the trick. Yeah. No, it's a good question. So there are techniques, and in fact, there's a whole course of techniques called differential equations, which I've taken and you guys haven't yet. So it's hard to solve differential equations, usually, but easy to verify whether or not you have a solution in front of you, right? So big question, you should still have y e to the negative 3x, but you should not have a question that it is a solution, right? That's something you can verify. Okay. So down here, let's come to this word solving. Rich, can you read starting at solving there?
Solving a differential equation means finding a formula on y equals stuff.
Okay, so that's what we just did. We solved the original differential equation with this miracle y equals e to the negative 3x. That's what it means to solve a differential equation, right? Okay, good. Let's move on to number 4. And we'll go back to Alex for 4. Okay, so the differential equations that we're going to solve in this class are all going to have this form. dy dx equals something with x's in it. We're looking for a function whose derivative is cosine of x minus 1. The good news is we've already learned how to solve problems like that. What are we seeking for cosine of x minus 1? an antiderivative, right? That's what this is asking for. Okay, so can we find an antiderivative of that guy? You bet. Y equals antiderivative of cosine. Is it sine or is it negative sine? Regular sine. Yeah, just be careful with those signs in front of sine and cosine. Antiderivative of minus 1 is minus 1x. And then if we want the most general solution, plus c. So how about we just pick a number here? So it just said what's a solution. So there's a solution, plus 17. And how are the different solutions related? They're all just different plus c's. Right? Those are all the solutions. Okay, on the next page, let's go to Sam for 5. Okay, so we solved the original problem already. Let's put the general solution here. We'll just rewrite it. So what was it? Sine of x minus x, and then generally plus c, right? So we're not just making up the 17, but we'll leave it general. But then we have this thing called an initial condition. We want to find the particular solution that's in this family that satisfies y of pi is equal to 1. That's just function notation, right? So pi replaces what letter? Is the x, and the 1 replaces the y. So let's just substitute that condition in. So we said the y becomes 1 equals sine of x becomes pi minus pi plus c. And there's an equation that we can use to solve for c. Okay, so let's solve this for c. 1 equals, how much is sine of pi? 0, and then subtract the pi, and then add the c. So c must be 1 plus pi, yeah? And so then our final answer, just recopying our original guy here, sine x minus x plus the c that we just found, 1 plus pi. Okay, and then just more vocabulary there. The original problem, the differential equation, and then the extra condition is called an initial value problem, those two pieces together. It's a problem that has an initial value given to you. Okay, I got a question here on number 6, because 6 looks an awful lot like something on the quiz you just took from me, right? Had we done stuff like this before the quiz? Not in this class. So how did I put this question on the quiz when we're only doing it today? Not this semester, though.
It was the last question.
It wasn't really this? It feels like this. All right, let's try this. And if I misplaced this question on the quiz, then I'll give everybody credit for it. So yeah. Right, all right. So when people saw this on the quiz, was it like a surprise? Or was it something that looked familiar and expected as you were preparing for this quiz?
Only because if you know that acceleration is the second derivative of distance,
yeah,
you can go back and forth.
And that's the idea, but we're only officially doing it here together, so I think I put this in the wrong spot. No, maybe. All right, I got to figure it out, gang. Sorry about that. Okay, so a little physics. We know that velocity is the derivative of distance or position. And then we've got one more set of words to fill in. Something is the derivative of something. Acceleration is the derivative of velocity. Okay, great. All right, let's go to Rob. Suppose.
The initial velocity of 74 meters per second, the velocity 0 meters per second. Taking gravity is negative 10 meters per second squared. Acceleration.
Okay, thank you. So, yeah, the more I think about this, the more I realize that I just misplaced that problem on the quiz. It shouldn't have been on there because we're only covering it together today. I'll figure it out. All right. Okay, so what's going on here? So if you know some physics, then this formula might look familiar to you. We're not going to use it, so don't bother writing it down. But H0, S0, what do you call it? S? S0. Okay, so there's maybe a familiar physics formula, one of the kind of fundamental ones that you might see on the very first day of Physics 1. Okay, but you know, like, why is it true? Maybe because Ted says so. No, it's not. It's because calculus says so. So we're going to ignore that guy, and we're just going to go from first principles, and we're going to build that exact thing. Like, that's going to be our final answer. Okay, so here's what we know. It says gravity is negative 10, negative 9.8, but we'll call it negative 10. So we'll start with A of t is negative 10. And then we're going to change that a to be the derivative of some other function. What is acceleration the derivative of? Velocity. So what that means is that v prime of t is equal to negative 10, just changing acceleration to be written as the derivative of velocity. And that equation is called what kind of equation? That's a differential equation because it's an equation involving the derivative of something, right? Okay, so what we want to do is, yeah, I think that's right. So then, so we can find the solution of that differential equation because all we're looking for is an antiderivative of negative 10. What's the general antiderivative of negative 10? Negative 10t, and then if we want to be general, we put plus c. And we just found an antiderivative, and what's a good name for it is v of t, right? So now we have our velocity formula with the plus c inside of it. Okay, and now we're going to find that c because we were given that initial condition. What was it up here? It said that v of 0 is 74. So let's use that right here. So we know that on the one hand, v of 0 is 74. On the other hand, you can just plug 0 in for that t. Negative 10 times 0 plus c. So how much is c? 74. Great. So c is 74, which means that this equation now becomes v of t equals negative 10t plus 74. Okay, and then we'll use another relationship we know from physics, that velocity is the derivative of what other function? This position. We call it distance before 2. So then we can change that guy. Let's go up back here to the top. So this guy then becomes that the derivative of position is that same negative 10t plus 74. Yeah, and then we'll just repeat. Everybody okay with that step? It's not a calculus thing per se, it's just that we know that the derivative of position is velocity. So we're just replacing it with notation. And look, another differential equation ready for us to solve. We solve it by finding an antiderivative of that right-hand side. So negative 10t, this is our power rule, becomes negative 10t to the 2, right? Add 1 to the power, and then divide, and then we'll reduce in a second. And then plus 74, what's our variable here is t, right? And then we'll be general plus c. Yeah, and then a good name for the antiderivative of s prime is s. So there you go. We just solved another differential equation, right? We found a solution, function s, that satisfied that differential equation. Okay, I think we were given enough info to pin down a particular value of c. We must have been given something about s. What does it say? It's up here now. S of 0 is 100. So that's what we're going to plug into this guy. So on the one hand, S of 0 is 100. On the other hand, we can throw 0 for all these t's. So negative 5 times nothing squared plus 74 times nothing plus c. So how much is c? 100. Great. So c is 100. So then our final solution to that differential equation, s of t is, so I'm just copying this guy. So now we're simplifying negative 5t squared plus 74t plus 100. So there's the solution to the differential equation. And again, I'll write down the physics formula that you might have seen on the very first day. Was this 1/2 at squared plus v0 times t plus s0. And that's the formula many of you said you know how to use. Okay, so 1/2 a, what was the acceleration? Negative 10, that was the given. So why is there a minus 5? Because it's half of negative 10. And this half, that half and that squared is part of a lot of physics formulas. I didn't make this connection when I took physics as a student myself, but if you see a half and a squared, it is almost certainly because somebody took two antiderivatives of a constant, right? Our negative 10 became negative 10t, which became negative 10t squared over 2. So that 1/2 and that t squared come from finding two antiderivatives. So like, I don't even know what this is the formula for, but 1/2 mv squared, what is that?
Kinetic energy.
I think that's it, 1/2 mv squared. 1/2 at squared is this guy. Yeah, but 1/2 mv squared. I don't know where that formula comes from, but I'd be willing to bet it's two antiderivatives of a constant, right? So if you see formulas with halves and squares in them from physics, it is almost certainly this idea. Okay, so I think that's good. And there was maybe one follow-up to this. What did it say at the end here? How fast is the object moving when it hits the ground? Okay, we can do that. When the object hits the ground, there's some very special characteristic it has. Acceleration, velocity, or position, which is the one that you know? The position, right? What is the position when it hits the ground? 0 is how we define 0. Okay, so then what we're going to do is set the position equal to 0. So this is the ground part of things. So 0 equals negative 5t squared plus 74t plus 100. Yeah, I don't know if that has nice solutions. Probably not. I heard somebody say Mathematica, so that seems like a good enough thing to use here. All right, so Wolfram alpha. What was it? 0 equals negative 5t squared plus 74t plus 100. All right, so there's the input. There's the parabola. There's the radical versions of things. Where's the approximate versions? Here we go. So it looks like 16-ish and negative 1-ish. Okay, so there are two answers. Let's see. So that means that negative 1.2 seconds into its journey, it hit the ground, and 16 seconds into its journey, it hit the ground. Well, we started the clock at 0, so we're ignoring that negative. So about 16.046 from Wolfram alpha. Okay, so we're just going to put dot, dot, dot. And we got t is, what was it, 16.046? Okay, so 16 seconds for it to come back and hit the ground. And the question finally said, what was its velocity? So what do we do with this 16? throw it into the velocity formula, right? So v of 16.046 equals, what was the velocity one? Negative 10 times t, right? And then plus the 74. All right, somebody help us out here. Something sounds fishy to me about that answer. Point 0.46. Great, that seems better. Meters per second. Yeah. Okay, so that's how fast it's going right before it hits the ground, negative 86 meters per second. What's that? You can go one more step back, but the acceleration's easy for any moment in time, right? Just because it's constant. But if it weren't, then yes, just go one step back. Okay, any questions on that? I appreciate you trying to bail me out. I think I just made a mistake.
Either way, it was still different than this.
It was, but I think this is exactly what I was asking you to do on the quiz. Last mistake of the semester. Last one. Yeah. I mean, for realsies this time. No chance. Should I pay you now? All right, activities start on page 47, next page. So raise a flag if I can help.